Welcome back. This is Structed, where we cover structural engineering concepts in plain English. I'm Eric, I'm your host, and I know it's been a long time. I had to move, I had a lot going on, but we're back. Today we are looking at what happens if you have a little gap between two beams. So on the left side here, we've got two beams, a smaller one and a larger one, stacked tight on top of each other. We're assuming zero friction between them, but no composite action either. They're just I1 plus I2. On the right side here, we've got the small upper beam actually suspended about a 1/4 inch up above the larger lower beam. So things are going to get a little different between the two. We are shooting for the allowable load at mid-span here that gives us L over 240 or 1 inch of deflection in both cases. So getting right into the no gap case. This is pretty straightforward. We've got I upper is equal to 5 inches to the fourth. I lower is equal to 45 inches to the fourth. We're going to say that we're using aluminum, which has an E, or a Young's modulus, of 10,000 KSI, or 10 million PSI. And we should all know or remember that the maximum deflection under a point load on a simple span is, of course, I don't remember it well, so I'm double checking here, PL cubed over 48 EI. For this no gap case, again, we're assuming that there is no friction going on, no composite action whatsoever, totally just I1 plus I2. The top beam is just free to sit there. All right, so that tells us we are actually interested here in I total equals I1 plus I2. So we are looking at, we're going to flip this around and find our P max. So P max is equal to, we're bringing all of this bottom over here. So delta allow, in this case, times 48 E aluminum times I upper plus I lower. And that's all going to be divided by L cubed. So plugging and chugging, we get ourselves here 1 inch, 48. It's just easier to keep it all in more basic units here. So this could be KSI, but let's not go that way. 5 plus 45 is 50 inches to the fourth. And that is all going to be over 240 inches cubed. 1 times 48 times 10, 123 times 50. It's going to be divided by 240 to the third power. So we get an allowable P max is equal to 1736.11, who cares? P max is equal to 1736 pounds. And that would be the full load there. If we were actually doing anything that was deflection critical, we might want to think about throwing a safety factor on there. But most of the time, deflection's more just for the the comfort of the occupants and things like that. So typically there is not a safety factor on deflections. Now, if we come back to our problem statement up here, 1/4 inch gap is a little bit more interesting. So if you think about it, we're applying our load directly to the smaller beam here. That smaller beam only has 10% of the total stiffness that we've got going on. So effectively what we're going to have going on is we're going to have, if we have a load displacement chart, let me see if I can actually get this right this time. We want to have load delta is typical convention, which seems backwards because really we're putting in a load and seeing our deflection, but that's fine. And at first, we're going to have a very shallow slope here. Very, very shallow. That's not nearly as shallow as it should be, but this is going to be our P initial, and that needs to give us 1/4 inch. So up until we make that 1/4 inch of deflection here, we have the stiffness of just the small upper beam. And remember, that only has 5 inches to the 4th going on there. Our actual slope is going to be dependent on more things than that. It's going to be the full stiffness. If we took this and solved out, I think it's 48 EI over L cubed would be our full stiffness, but the 48, the E, and the L cubed are all remaining the same. The only thing we're going to transition from at this point is we're going to add a whole bunch of stiffness. So when we go from, when we hit this 1/4 inch point, and this is all still assuming small deflections, homogeneous isotropic, linear elastic materials, all that good stuff we usually use for Euler-Bernoulli beam theory. Once we hit this 1/4 inch, we're engaging the whole thing and our stiffness goes up like a rocket. This stiffness here should be 10 times this because we're looking at 50 inches to the 4th. And remember, everything else remains the same. We're not changing the length of our beam. We're not changing the material of our beam. Once those contact each other, we're just getting a ton more of our moment of inertia brought into play. And we're still, again, we're using the same assumptions. We've got no composite action. We've got no friction between the beams. It's all a bit contrived, but point being, if we just assume right out of the gate that we're using 50 inches to the 4th for this whole thing, we're effectively coming up along a path that looks like this. We're using this stiffness right away. Apologize for the dog tags jingling in the background. We're using this stiffness with that 50 inches to the 4th right away, and we're going to overstate drastically our allowable load because by the time we get up here to our 1 inch mark, there's going to be this big difference between our two lines, which is going to have this with a wildly higher load. So you remember we were at 1,736 pounds. Let's see what we get on this one. So it becomes a two-part problem here. We need to find out effectively what load does it take to deflect us a 1/4 inch on just our nice little beam, and then what load do we need for the remaining 3/4 inches of deflection. If I can capture this all on here. So we're going for P 1/4 inch, we'll call it, is equal to 0.25 inches, 48. Everything is the same here except for we've got a 1/4 inch in there and we've got 5 in for the I value. PSI times 5 inches to the 4th over 240 inches cubed. And if I had my brain on better, I could tell you that this is 1/10. I'd be able to figure that out a little quicker. But we're going to just plug and chug it straight on through. Times 48 times 10, 123, 123 times 5. Divide by 240 cubed. It only took 43 pounds. 43.4 pounds here. 43.4 pounds to deflect us that first 1/4 inch. All right. That's tiny. That should have been, quote unquote, a quarter of this, but it's not because we have so much less stiff of a beam for that first quarter inch of travel. Now, we know that P initial is equal to 43.4 pounds. And then we need to come up with the remaining 3/4 inches of deflection with the full 50 inches to the fourth in there. So P 3/4 inches, 0.75 inches times 48, 10, 1, 2, 3, 1, 2, 3 psi, 50 inches to the fourth. And this should legitimately be just 3/4 of that 1736. We'll plug it through just to make sure I'm not fat fingering anything at all. Piper, go upstairs. Apologize, the dog decided now is a great time to chase her tail. Times 50. 1302, that sure looks like 3/4 of what we had before. 2 pounds. So our total for this case is just 1302 plus 43.4. So I'm going to go back in the memory and grab that. We've got 1345.5 pounds. And you remember before we had P no gap was 1736 pounds. So because we left that 1/4 inch gap in there, our allowable load has dropped. We only get that P allow with the gap is all the way down here times no gap. So we lost 22.5% of our allowable deflection capacity to that gap. So it matters. It matters a lot. And the difference here is only going to get bigger with the larger difference between your stiffnesses. Obviously, if you had half of your I value in the first one here, your change in slope is just going to be a doubling here instead of a 10 times. So you're going to have a lot less of this free travel of your less stiff member. So with that, if you check the link in the description below, excuse me, check the link in the description below for, I believe it's 15% off on everything from PPI. PPI2pass.com sets you up for success on your PE or SE exams. I'm also studying for the SE right now. That's part of why I've been gone so long. So thank you guys all so much. I've missed you. Please drop a like, share, comment below. Let me know what you want to learn about. Thank you so much. Bye.